Oh yeah, absolutely.
Did you guys ever see those the Out of Vines videos?
Yes.
Yeah. You see that one video about the guy? Somebody calls him لأن اتأخر. قل له وينك يا زلمة؟ But then they show the guy answering. هو نايم. يكون عندك بعد 5 دقايق. هو لسه نايم. That wasn't me. والله كنت في الطريق لما حكيت معك.
لا يوم
يعني خلاص يعني يقول لك بعد 5 دقايق كنت already في الطريق. طيب بسم الله. I wish we had a better forum because we don't have a board or something for me to draw pictures on. Sam knows I love to draw pictures. We get in trouble for drawing pictures, I don't know yet. So,
I think I was gonna, maybe we talk a little bit in general about communication. You know, just, you know, many times we find that engineers coming out of school tend to be very narrowly focused. And when we get out in the market, we have no idea how our trade and our profession is going to be used. So in that respect, maybe we talk a little bit about history today, talk a little bit about where communication is going, and where we think, you know, many of the skills of the Shabab, alhamdulillah, where they might fit in the future, inshallah. And I think that would be, and then I think we follow it up, inshallah, with a more detailed, we start, you know, between Sammy and yourself and I, maybe we can create a small 101, 201, 301, and then masters.
Absolutely. Absolutely. To be honest, I'm sorry, so I thought it was going to be a smaller, so I just prepared for, I didn't prepare, but I was mentally prepared for just some, like when you and I sat at USC, just to go through some drawings and things. But so inshallah it'll be beneficial still, but stop me any time when we're talking, and so I can clarify and add detail where I'm missing detail. When you look at any communication system, it has several main components. I can't say how many components until we talk through them as they come back. We talk about a communication system. You're talking about me talking to you. I have some information. I'm relaying it to you. Today we're talking. You're looking at me. I'm looking at you. I'm saying things. Right now you're the receiver of the sound. So I transmit it from my mouth. First, the information develops somewhere. It's sent to my mouth. I send it to you. And then you're receiving it with your ears. And then your ears take it in. And then your brain processes it. And then you decide what to do with that information. So we're a self-contained communication system. We have all different types of sensors at the same time. While I'm talking, you're listening to me, and that's the main thing that you're processing, but everybody is also looking and making comments in their mind and saying, everybody, sensors شغال. It's a little bit hot. People are a little uncomfortable with that. His communication system these days is a lot more than it used to. The first communication system people think about, they think about something like the telegraph. Right, a long time ago, people had a need because I think it was Samuel Morse. Right, do you guys remember Samuel Morse, the guy who did the Morse code? He had a need to send some messages somewhere, and he got tired of the communication system. The old system, get that letter, write it out, put it in an envelope, get the guy on the horse before the cars, let him send it across the country. وصلت الرسالة, okay, by the time ترجع الرسالة تلقاني إنه ولا أبصر شو, and he didn't even hear what's going on. Communication was too slow. I don't know what would you say that baud rate was. It was a slow baud rate. I don't know what that communication rate is. How many bits per second? How many bits per days? It was a very number of bits per days.
With pigeon or without pigeon?
Without pigeon kind of advanced, yeah. Yeah, like اللي كان عنده بيقدر يربي pigeons and raise them and teach them the right way of going and coming back and not getting lost and not stopping along the way. For the issues of communication are exactly the same. The same problems to our Morse, the same problems to our pigeons, is how do I get my information that I want from where I want it to go to where from where I want it to emanate from where I want it to start from, to where I want it to go. How do I get it there? And how do I get that information there reliably? And how do I know that it got there? And how do I do it in the quickest time possible? And how do I use the least resources to do it? in the most cost-effective way, right? So if I have this letter, it costs the guy some time to write it. It costs him some time to put it in an envelope. It costs him some time to find the guy who has a horse. He has to pay the guy who has the horse. It takes time for the letter to get there. He has to wait a few days before the letter gets there, and he has to wait a few more days if the guy comes back right away to find out that the letter get there and have an acknowledgement that the letter got there. And then to find out the response for the letter, he has to wait for the guy to write it, and then same sort of thing. But if there's any miscommunication between them, it'll take multiple days, multiple months, multiple weeks before he finds out that the information was correct and that the other party understood what they're saying. Same exact problem. When we're talking, and I'm trying to convey a message, it's the same sort of thing. It might be happening faster and on the fly to make sure that the communication that I have for you guys is getting to you, and that I'm sensing the right response, or I'm understanding your questions, I'm understanding what it is that you understood or didn't understand from the message that I had. So communication systems are all about conveying information in the most efficient method time-wise, and the most efficient method error-wise, keeping it error-free, and in the most cost-effective way. Sometimes cost-effective also means size. And if you guys, have you seen antennas? You know, you might look at a tower. You ever see those big, huge, round, dish-looking things on these towers? The bigger the antenna generally means the more power that it can handle, the more power it can transmit, and it means the more directive it is. That means, like, also in communications, I don't want to talk to everybody sometimes. Maybe I just want to, what's your name, brother?
Asa.
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 Asa. So maybe I only want to talk to Asa. So I have to figure out a way, if I'm in this room, how can I only talk to Asa and not anybody else? Maybe him and I can start speaking a foreign language, and the rest of you guys will be left out. First I have to find out if anybody else knows that foreign language. But there's ways that people can direct their information. And it's exactly the same problem as the problem with a foreign language. We can start speaking a foreign language, and we can go to a different frequency that nobody else understands. We can be on a different wavelength. You don't have to think of wavelength that except for us, or they don't know that we're on it. Hatta on top of that, if we know that people understand our wavelength, we can decide to start speaking in code. We can start using our letters backwards. I'm going to do you guys ever hear of pig Latin? Or some just switching the first letter and the last letter. So as to try to not have people hear what they're saying, they would do something like that. Same sort of thing going back to the guy in the horse, on the horse sending the letter. What they would do sometimes, they would put a seal on the envelope. And he wants to make sure the guy carrying the letter doesn't open it. And so that the guy who gets it on the other side can confirm, nobody opened this letter, nobody tampered with it, nobody's seen what's inside it, because it's probably sensitive, something. Something in that letter he doesn't want anybody else to know about, and if somebody did find out, it would harm him and harm other people around him. Same concepts apply. We didn't mention security, so security would be a very, very big part of communication systems. So after Morse, and this was all done on the wire, and his information was all just, let's have a convention. Just have a convention together. If I tap once, and it's short, that means the letter A method. If I tap twice, two short ones, maybe that's, I don't know Morse code, I'm making up what Morse code is, but it's something like this. It's a convention. We decide together what it means, and that's what it is. Telegraph, the lines started going up everywhere. Setting up these telegraphs, because suddenly now we can communicate, I can save some money. Problem was the lines weren't everywhere. They had to start putting up lines, and infrastructure started getting it. And so then they get to a point where everybody's enjoying this telegraph, sending telegraphs. Main people who usually benefit from communications, with military people, because they're the ones who have all the tax money. They set up the infrastructure, with the rest of the people that have to wait. Because of the GPS, the same thing. We're working on GPS antennas back in college, more than 20 years ago now. For the first consumers, the first consumers of a GPS antenna is kind of the military. And GPS was closed. No one could use it. Sam knows that no one could use GPS except for the military back then. GPS about on global positioning satellite system. And consumers didn't have access to it because it was a little too sensitive for someone to be able to see and know and use the information that comes from a satellite and to be able to tap into a satellite. Security wasn't as good as it is today. There's lots of reasons why. Being able to have a sensor in the sky and look down on things and create an entire map, and to be able to sense live and see what's happening on the Earth moment by moment. It's a very sensitive thing. The GPS was only about positioning, but that same concept applies of those taps. للين على taps. That today, modern, we can say that that's the digital system, digital communication. There's what's called analog communications and there's digital communications. Digital communications is Morse, is enough. And you and I can decide that any time on my voltage for the electrical engineers, if I decided that the way I'm going to communicate with somebody is I'm going to take the voltage on this output and it might start at 5 volts. And at 5 volts is considered high, and anything, let's create some thresholds from 0 to 5, right? So maybe anything above 10%, anything above 10% below the max is considered high. So anything above 4.5 volts is high. Anything below, let's say, half a volt is considered low. So we could agree, to communicate with each other. We'll just start translating Morse. We'll just use his code. So anytime on this voltage line between us, when I want to send something high and say that it was a tap, for the duration that I want to make that tap, I would keep the voltage high. And then whenever I want to send it low, I would ground it through some type of a load so I don't use lots and lots of current if I send it directly to ground. You ground it, that'll be your 0. So that same concept, that digital, meaning you're just doing zeros and ones, right? The 5 volts is the 1, well, 0 volts is the 0. So it's kind of an on-off, a binary, digital, binary, however you want to look at it. It starts off binary, just zeros and ones, and then you extend the duration of the 1, you extend the duration of the 0, and that's a new variable. It's all about finding ways to differentiate these zeros and ones, whether it's in time, whether it's in power, whether it's finding new steps in between, so مش بس 0 and 5. If I'm very accurate and I have a good sensor, maybe I can start using 4.5 also as a dividing point. So maybe I can have 2 high points, 4.5 and 5. Maybe I can do 4 and 3.5 and 3. Maybe each one of those can mean something. Maybe I can start going 1/4 dB steps. Maybe I can go in 1/10 of a microvolt and step. There's so many ways to cut and slice. Wa alaikum salam. Well, we already had our quiz, so there's so many ways to slice the information to give you an opportunity to send more data during the same period of time. So the goal is to get the information to you in the shortest period of time in the most secure way, and to have everybody understand. So in the very beginning, does everybody understand what we've talked about so far? So if you didn't have, if I don't have the ability to see you in front of me and you don't have the ability to hear me, then we have to somehow get that information converted to a different format like that letter. So we convert the actual message into written form, and then we deliver. And then the other side has to take it in written form, convert it to something that we understand, and then it becomes information. So Morse did, going back to Morse, he did exactly that. First he took the information, he converted it to these tapped signals of voltages, and then on the other side it came out in tapped voltages, and then someone had to know that translation, they would translate. So today, in communication systems where people are not present, and maybe we'll first talk about wireless, because we kind of covered wired in a really weird way. But wireless, it starts off with the same concept. Someone has a message, and they want to send it to the other side. So how do we send it to the other side? First, you come up with your message that you want to send, and then you have to convert it to a form that is okay being sent over the air in a wireless fashion. So how come I don't hear what people are saying? People are on cell phones right now talking to people, but I can't hear what everybody's saying. There's probably 1,000 people on phone calls on the towers that are around us, but we can't hear what these guys are saying. And that all has to do with the wavelengths that we were talking about. We can hear things that are in the kilohertz, right? I forgot what our hearing range, if anybody remembers, is something like 20 kilohertz to, I forgot what the range of hearing. But we have a range of hearing in the very low frequency. Frequency, when you think about frequency, it just means how often, if you were to track the peak of the signal, and if it was repeatable, the frequency means how quickly does it, in time, come back to the same thing. So if you're looking at a sine, the classic signal that everybody looked at when we were in college, when you tried to understand frequency and phase and time, or period, if you started with a sine wave, to know the frequency, you would start with the peak, or you pick one peak, or a minimum, or the same, or somewhere in the middle, and you say, when does this peak return? So you'd measure the time between the first peak and the second peak, and you say, that's my period. That's how long it takes for this to repeat. And then your frequency is, how often does it happen in a second? So you invert that, and you get your frequency, which is hertz, which is events per second, the frequency, how frequent something happens. And so, as we talked about before, when you're doing these different frequencies, that's one way to differentiate signals from one another. That's one way to differentiate and keep people from interfering with one another. We'll talk about interference and all these things, hopefully, inshallah, today. So, you need to get your information converted from your thoughts, from your paper, from your computer, whatever it is. It's got to get converted into these types of signals. Somewhere in the world, someone agreed on, when I type A on my keyboard, it means this in ASCII, right? The ASCII codes for what these letters mean, and someone had agreed at that time that this is what we're all going to do. We're all going to agree with that. This is what this is going to do. So every letter can be converted to a bit sequence from that ASCII. Everything that we type, you convert it to a bit sequence. Now, these bit sequences are depending on how fine I want my voice. So how do I want people to hear me on the other side? Do I want them to hear me exactly the way I speak, covering all the, so as we said, our sounds that we can hear, at least that we know about, that can be emanated from our voice, are in the kilohertz of range, right? And it's a broad range. If you had a spectrum analyzer, and I wish we did, where you can listen to you can see yourself speaking. You can see yourself speaking. You'll see that as you speak, you're using low frequencies and high frequencies within that 20 to 60 kilohertz, whatever the range is. Maybe somebody can look it up so I can stop using the wrong one. Did you look it up already?
No, but that's.
Oh, you got, okay, perfect. So as you're speaking, you'll see that you're changing amplitude. You're changing the amplitude of your voice. It's getting higher and lower in amplitude. And you're also changing the frequency of your voice. Sometimes you're using a really deep voice, low frequency. And sometimes you use a high-pitched voice, a higher-pitched voice, and the frequency goes up. And so the first thing to do when you're trying to send voice over somewhere else and you want someone else to hear you is to sample your voice and make it into a digital signal. Yeah, I'm going to sample in time. I'm going to take a time slot, a time capture of, let's say, 1 second of this speech. So I would start sampling at a certain rate. You guys maybe we'll talk about Nyquist another time. You're sampling at a certain rate to make sure that you capture enough information to get the quality of signal that you want on the other side. And obviously the more samples you take, the better the resolution. Resolution just means more samples. The better resolution of the samples that you take, the better quality, the better chance of having the person on the other side hear you as the people who are here might hear you. So if I want to digitize and send it somewhere else, which is what sampling is digitizing, taking a sample of the frequency over time, getting a sample for what's the frequency, what's the amplitude of my signal. That would be the information in a voice signal. You would take something like amplitude, what was the volume that I was speaking and what tone came out at this exact second. And so you do that. You take sample 1, sample 2, sample 3, sample 4. You can imagine if someone took, if I spoke for 1 hour and people took 3 samples only, at the beginning, middle, and the end, they won't be able to understand anything that I said, right? They just took a sample, they might hear, that's all they would hear. They heard 3 different frequencies at those times, or mixtures of those frequencies, that's all they would hear. But the more samples they start taking, it's just like the megapixels, exactly like the megapixels, which is another form of data that you want to transfer to the other side. If someone had a picture this big, and it was just black like it is today, and there was no light in the room, there was no reflections, 1 sample would be enough to cover this whole picture, black. You send information black, they fill it with black, they're perfectly happy. But if there were reflections like this, then it's not a super high resolution picture. It's got some resolution in it, right? You might be able to take 1 sample every inch, or every square 6 inches or something, and you would still have a pretty good picture on the other side. But if we had a picture of, say, this sajada, right? If you were to take a picture of this carpet, it's a little bit more detailed. And so if you wanted to capture it without having something, like we have this area here, it's got some brown and it's got some green, but in the middle it's got a transition, it's got some pink in there. So if your samples are not fine enough, let's say your samples were just like this, you're not going to be able to get a good picture, right? The pixels means that they're breaking up a picture into little pixels. And so the smaller the pixel, the more likely you are to capture it exactly as it is. The bigger the pixels, if it's a fine resolution picture, the less likely you are to capture the true nature of that picture, right? So the first part in the communication system is converting your information to some format that's going to be electrical very shortly. You got to convert it to something electrical. If it's sound, you have transducers, right? They take the sound and they create electrical pulses from it. If it's video, or I'm sorry, if it's a picture, if it's pictures, what we do with pictures is you have to create the pixels, and each pixel, and I'm not a video or a picture expert, but the concept is you take the picture and you cut it up into these pixels, and each pixel represents a color. Each pixel represents a color, and depending on what you have in your tool bag on the other side to represent those colors and translate those colors, then you would be able to do that. And it's all about coding at that time. That's what they call codecs, right? Whether it's a voice coder, or it's a video coder, or like a picture coder. You know, like, you know, you guys use JPEGs and you use MPEGs and you use these things. All those are about different conventions for what's my resolution going to be. How much resolution can I have? What type of correction, what kind of estimation am I going to use to get this picture when I send it to the other side to look just like it? If people don't care how good it is, or if they don't want to pay for it, or if they have cheap equipment on the other side, the translator has a different problem. We'll talk about the receiving side. So first job, convert your information to a format that will allow it to be coded. When I say color red in this codec, it means I'm going to transmit frequency Y in this short duration on with this amplitude method. However, so as we said before, information can be coded in amplitude of voltages. It can be coded in the frequency of the voltage. Those are 2 things that we mentioned so far. You can code in frequency, and you can code in amplitude of a signal. So you can decide in the method, and you want to do تفضل شربوا شاي. I don't want to drink tea while I'm speaking. تفضل. You can decide to know if all I have is this voltage regulator, and I want to make a communication system, then voltage is the only thing you have to represent, and you got to create a code that says this voltage means this means that, and then you can become creative. If it's still the only thing you have, you can say, okay, I can say I'm going to have a repeating sequence. I'm going to say high-low, that's fast, that happens in a microsecond. That means something, instead of just saying high and low means something, because that's just like on and off. Like if you have a switch, on and off. On is 1, off is 0. If I want to send, if that's the only thing I have on and off, then I have to find combinations of on and off to represent 26 things if I want to represent 26 letters, right? If I want to be able to send messages, each one needs a letter. The sequence that I have with on and off, the most primitive one, depending on how many seconds you leave it on and how many seconds you leave it off, it means different things. Just on, if we just wanted to use on. You leave it on for 1 second means A, 2 seconds means B, 3, okay, until you reach 26, but that takes a long time. It's not a very smart way of coding, because it just takes forever for you to do the sampling and the coding and the decoding on the other side. But maybe a smarter way would be, if I was able to turn it off and on very fast, if I turn it on and off within 1 microsecond, that means A. So instead of it taking me 26 seconds to get to Z, maybe I can come up with even a faster way. If I do on-off and then off-on together in 2 microseconds, maybe that means Z. So I can get to any letter that I want, maybe in 2 microseconds of code. So that's the general problem you're solving first, is trying to convert the information into some kind of a code that is electrically based, whether it's voice with the transducer converting your sound, the vibrations from your voice at the frequencies that the brother was showing on the voice analyzer. And now it's time for us to take it to a different medium. It's still very, very low frequency, what we're talking about. Very low frequency. And a lot of times, you'll hear it described as what's called baseband. Baseband frequency. When you're at a really low frequency that contains live information. And if somebody took this signal, right now that we just decoded from the video, or coded from the video, or recoded from voice, it's so simple for them to just take that signal that we took from the speaker, or from the microphone, and convert it to electrical. If I took that same signal, because it's just showing the amplitude and the frequency of my voice, it's so simple, these transducers. If I plugged it back into a speaker, somebody would be able to hear it. So it's totally uncoded, totally insecure, totally easy for someone to just tap 2 wires, the high and the low voltage, and just plug them into a speaker. It's probably a little weak for most speakers, but you might need an amplifier in front of it. And everything's okay. They plug those into a speaker, they'll be able to decode it right away. They'll be able to hear what you were saying. So that's where we are today, right now, in terms of figuring out two types of, or several types of information: voice, data, video. It's all about coding the information you want and preparing it in this low frequency baseband signal. But as we said, how come I can't just plug in and hear what people are talking about? How come I can't hear all these signals? How come I can't see pictures flying in the air and I'm shaking? Why? Why can't I hear those? Those are coming off at really, really low frequencies, but that's not what they're transmitting. Leish, I'll give you an example. So if you guys remember resonating, did anybody take any electromagnetics or like transmission lines? Yet anybody take anything about transmission lines or radiating structures? Going back to the days of physics, everybody took physics, right? So going back to that same concept of wavelength and frequency. Remember the relationship, it's probably one of the most important relationships you learned early on in physics, extremely important relationship, which is if you have the certain frequency, what are the units of frequency? It's 1 per second. Hertz means number of cycles per second that something repeats, right? And speed is, we measure that in distance over time. So that might be something like a meters per second, yeah? Wavelength is you can measure that in time to say this is how long it takes, or we can measure it in distance. The most common convention is that we measure those in distance, right? So if you had something like your frequency and your wavelength, we get something that's called the speed of light. Speed of light. So the speed of light, c, which is the units of meters per second, is equal to the frequency of your signal time, and the wavelength. The frequency times the wavelength. Yeah, if you had, so from this relationship, just to start building some intuition around it, if we had the frequency of a signal and it was in free space, yeah, just free space, we can calculate how big of a wavelength. So imagine that someone was, and just maybe someone can help me with some calculations here on the fly. So speed of light is 3.0 times 10 to the 8th meters per second, right? So if I had a signal that was running at, let's say, 100 kilohertz, right? So I want to find out how big is my wavelength if I have a frequency that's 100 kilohertz. Can someone calculate that for me? We have a bunch of calculators. Don't make me take out mine.
Or 300 maybe.
Yeah, so 3 times 10 to the 8th meters per second. So you get your C equals Fy. I want F lambda, so I want to know what lambda is. What's my wavelength? So take your 3 times 10 to the 8th meters per second and divide it by the frequency in hertz. Not so I'm giving you a frequency in kilohertz. You got to convert it to hertz. ايش هذا بحسب؟ Okay, نحسب شو نسوي؟
You said 100,000 kilohertz?
100 kilohertz.
Oh, 100. That's not too far.
3,000.
3,000 watts.
Meter.
Somebody have it? What was it?
3,000 meters.
So if we start with can't find the calculator. It's buried in this iPhone تبعتك. Seems like it's a nice one. You turn it this way.
Yeah, there you go. Yeah.
It's the scientific calculator. Eventually. Unless I like the old system better. Anyway, so we have three. Well, let's just do it in our heads. That's not the format of this one. 3 times 10 to the 8th, right? And you're dividing it by 300 kilohertz. We said, well, look at this kilohertz.
100.
100 kilohertz to make it easy for division. That's why I chose 100, yeah. So 100, which is the same as 1 times 10 to the 5th, right? So 8 minus 5, 3. So somebody said it was
3,000.
3,000, right? So 3,000 meters. 3,000 meters. So that's the wavelength of this thing. It's huge. The wavelength of the Ekman is just like, it's huge. It's like 3,000 meters. That's 3 kilometers. 3 kilometers. So that's not a very, and so why are we concerned about something like that? Is because if I wanted something to resonate, if I wanted something to resonate at that rate, usually resonators have to be a quarter, in order to be an efficient resonator, it should be a quarter of the wavelength at most. Something like, if you want it to be efficient. So if I wanted something to resonate at 100 kilohertz, that means I need that thing to be at least a quarter of the 3 kilometers, or of the 3 kilometers. So let's just say it needed to be, it needed to be something like 800 meters. And we choose a quarter wavelength. That's the size, the dimension of your antenna. So I need now, if I want to transmit that frequency of 100 hertz, 100 kilohertz, I need an antenna that's 800 meters long and 800 meters wide. That's not pretty practical. Have you ever seen an antenna on a tower that big, from all the towers you guys have deployed? Never. It's not very practical. So no one's out there transmitting 100 kilohertz today in normal communications. The military does crazy things, but normally in commercially available networks, you will not see anybody transmitting 100 kilohertz. Right? So our voice, we said, is somewhere lower than that, so no one's transmitting our voice directly. It would cause a lot of problems anyways, because we would be hearing everybody talking if that's what people had to do, was to send signals in 100 kilohertz. And there would be all sorts of interference and so on. So what people do is they take that baseband information from the 100 kilohertz and we upconvert it. We'll talk just a little bit about circuits and how that's done, just really high level. But we upconvert that signal to something which identifies a frequency level. So what happens when we go from, instead of 100 kilohertz for your frequency, what if I went to 1 gigahertz, which is 1 times 10 to the 9th? A gig is 1 times 10 to the 9th. So if I take 3 times 10 to the 8th and divide it by 1 times 10 to the 9th, I suddenly get something that's smaller than a meter, right? 8 minus 9, you get minus 1, so it's 3 times 10 to the minus 1, right? So now you got something smaller than a meter for the wavelength. It's getting more reasonable. So if you see something that's 1 gigahertz, the antennas are starting to get to a third of a meter in wavelength, which means if I wanted to do a quarter of that, it's 1/12 of a meter. Right? So let's just say it's 1/10 of a meter, which means that now a gigahertz, a quarter wavelength, what's a tenth of a meter? Because I'm still an inch after now. 1/10 of a meter, and we're talking like what is it?
3-4 inches.
10 centimeters times 2.54 divided by 2.5. How many inches?
3,
Oh, you want
4 inches.
Yeah.
Divided by
4 inches.
2.5.
2.54, right? Yeah. But anyways, cutting and code, it's 3 inches or something, right? Or 5 inches. Let's just say it's 5 inches or 6 inches. So now the quarter wavelength is this big. So you can make an antenna that its dimensions for radiating. As we said, we'll talk about radiating structures later. But this is the gist of it is to say, if you want something, you want to send something wirelessly at depending on the frequency you're at, your wavelength, your quarter wavelength, which is how big you need your wire to be that actually does the radiating. How big of a gap you need between some electrical things that creates this radiating element. It would be something on that order, right? So now suddenly we brought it down in the 1 gigahertz, so now we're talking 5-6 inches for 1 gigahertz. And so now we keep scaling. If you go to 10 gigahertz, it can be smaller and smaller, those radiating elements. Then you run into different challenges we can talk about much later time. So you convert this baseband signal that contains the actual information to this higher frequency, so you can get the wavelength in this reasonable range of radiating devices. So you can send it over there. So you've converted it over, and we haven't talked about at all the coding or the security or anything like that just yet. We're just going to send a dumb signal to the other side, and we'll come back and fix the security in a minute. So on the one side, so we converted to 1 gig. We created an antenna, that's maybe half a foot in diameter or something like that to make it efficient, and it's reasonable size to be put on a tower for a single device. You send that signal to the other side now. Now, as you know, each of us, maybe when we're younger, our hearing is unknown exactly how good the quality of our hearing is, but some people can hear better than others, right? Some people can understand people's dialects better than others. Some people can understand more languages than others. Some people can, like if you're not used to listening to someone who has a heavy Indian accent, maybe you won't be able to understand a person who has a heavy Indian accent. But if we first focus on just, given that we all have the ability to decode the information equally, but some of us just can't hear as well as others, then we get to talk about something called sensitivity on a receiver. Right? So I transmitted it. I was the owner of the information. I transmitted it over my antenna, and it's going to a remote location, because somebody on the other side has to have a receiver. And the receiver has the same sort of information, just in reverse to what we just did on the transmit side. So he has to have the antenna first, the device that will resonate when he hears the frequency that I sent. So he can't use that, or he could if he wanted, that 800 meter antenna that we talked about. But if he wants to be efficient and reasonable, Adami, use the 5-6 inch antenna that he created. It'll resonate when it hears that frequency. It creates a resonance that generates some power for the radio. So he'll take the RF energy in it, which is what we call the radio frequency. I'm sorry, the radio frequency. We refer to that in short by saying RF for its initials. It'll take this RF energy that we just now sent at 1 gigahertz over the air, takes that information, and now the fun begins. No one can hear a gigahertz, as we said. So you got to bring it back down to the baseband, which we said is in the hundreds of kilohertz, or like near 100 kilohertz for a voice, a little bit lower than that, right? So you bring it back down, and now it's like, okay, what is he going to do with all these electrical signals? He has signals that are changing in frequency. If you put it on a scope, the voice, just like the brother did for us a little while ago, you can see the amplitude is changing and you see the frequencies change. It's like, what am I going to do with this? Well, that's simple. Decoding or getting that back to its original form, you just plug that into a speaker and he's done. He's done. Sometimes it's not as simple because the signal gets messed up. If it's a very long distance, the signal might not look as good because now it's starting to get, it traveled a very long distance and the actual RF signal was getting very, very small. And as this RF signal, as it, maybe I should have talked about this first, but let me just continue with this train of thought and we can come back. But as the signal travels, as an RF signal travels, it's going to get smaller and smaller and smaller and smaller and smaller as it goes along. So you can imagine that if I wanted to send a signal from my antenna, if I was only sending it across the street, it'll get there pretty strong. Just like my voice, if Hussam was on the other side and I wanted him to hear me, I could yell and Hussam could hear me. If Hussam doubled his distance and went, you know, instead of being 100 meters away from me, he went 200 meters away from me. If Hussam's hearing was twice as good, at least as what it took for him to hear me here, then he could hear me over there. My voice didn't stop. It's just getting smaller and smaller and smaller in amplitude. It fades, but it's fading, so he raises a good point. If it was just a direct signal that Hussam was able to hear from me, the amplitude would be getting smaller, but there's a really other interesting thing that happens in the world, which is called fading. It means when you send things over the air, it's not like in the wire, where it's just, it's a very clean environment. The wire has nowhere to go. That's not how the wire, some wires are bad and they do actually leak and accept interference from the outside when they're not made well. But when we're talking about just sending it across the street to Hussam, it's an open air environment, there might be echoes. We can easily echo, it goes from this wall, comes back to this wall, something signal goes from here and goes to the other side. These signals add up. And sometimes they add up in a bad way and makes it louder, in a good way, and Hussam can hear me because it's louder. Sometimes it's in a bad way. If he's in the right spot, those signals add up and they actually subtract and they cancel. And you won't be able to hear very well on the other side. So my signal, my voice is not dead. It's wrapping around the world probably several times, and it's probably still here. Someone who says, like, you know, maybe Hussam said something 20 years ago, it's still here. It's just somewhere flying around. It's getting smaller and smaller as, you know, time goes on, and as it travels further, it's just getting smaller in amplitude. And you need someone who can hear really, really well to hear it. If his hearing was that good, we would have all went crazy. If we can continue to hear what someone said 5 years ago, and it just keeps coming back, and you hear it over and over again, it's coming at the speed of light, we would just be totally nuts, right? It would be kind of cool. What was that one movie where someone was doing that? They're trying to create a device.
The Rasul said so, sallallahu alaihi wasallam. He said, I can hear people in the grave.
Yeah.
So
Hussam wants us to create a device. We're going to try to sense and see what people are saying in the grave. It's got to be at a different frequency. It's got to be at a different frequency. We've been thinking about the spectrum analyzer to hear what's going on at those frequencies. It has to be. It's just some other frequency. We just don't know what it is. And then we got to figure out how to decode it. It's probably modulated in a different way. It's a different something.
I read like about like some scientists try actually to reconstruct older signals, like from people who were like a couple of hundred years, so we can hear that. You know.
Yeah, so it's the same problem. It's the same problem. So as the signals go further away from you, they just get weaker in power. And so on top of it, people are creating new signals, and they're all going around. So if it's the same frequency, this is a good place to stop and talk about something really high-level system. So what makes me able to hear you when you talk and you to hear me when I talk? So we're all pretty much on the same frequency today. Now we all speak, you know, the same language, and frequency-wise, there's not a big difference between our voices. Maybe someone who's an expert can keep his voice in the low and speak in a very deep voice the whole time, and we'll be able to tell. We can make it out if everybody in the room was talking. If everybody in the room was talking at the same time, we can make that in mayas and separate between the voices. If we're all speaking at the same volume, and no one's yelling and someone's keeping down. But if someone was yelling, that's a way to differentiate. We can tell the guy who's speaking loudest, right? And then we can tell the guys who are speaking with the highest frequency. And we can tell the guys who are speaking with the lowest frequency. And we can tell the guys who are changing a lot when they're coming in and out, they're changing frequencies very fast. Those are some of the differentiators that we have. But so the first one that we talked about is the actual amplitude. The amplitude. If somebody's talking very loud and someone's talking very low, will you be able to understand? Who will you be able to understand? Who can you hear? The loud guy, right? You'll be able to hear the loud guy. So let's say that Isa, right? You were talking, and somebody from here, Ahmed was talking, and if you guys were talking at with the same volume, but I was looking at you, so my ears pointed that way. If it was the same volume and same frequency, I'd probably be able to hear him and decode what he's saying and understand what he's saying more than I can if I was able to hear you. But if you were both standing there, speaking with the same volume, I wouldn't be able to understand either one of you. Same volume, same frequency, I wouldn't be able to make it out. So that's a different technique in antennas that we call directivity. If I decide I don't want to hear you, then I will make sure that the antenna, the radiating element, I won't let it face you. I'll try to make it narrow. This is called something, a very advanced technique in the last 20 years that people do with antennas. I don't want to hear everybody in the room. I want to zoom and focus, or I want to zoom and focus for whoever I want to talk to. I just want to talk to him. I just want to zoom and focus on the guy that I want to talk to. So the antenna ممكن تكون very, very receptive and open to the world, because the type of communication he's looking for, he wants to hear everyone. Anyone who might talk, I want to make him. I want to hear anyone who might talk. I'm not worried about people interfering because maybe I'm coordinating it. Maybe I'm the director. أنا بقولكم okay. ما حدا يحكي إلا فايدة. Then in the case like that, I have a big antenna, and no, I want to hear everybody. I don't want to turn and face you also and make sure I point exactly, just to hear only the person because someone else might be talking. لا احنا مرتبين في director. The director بيقول دورك. Okay, ما حدا يحكي okay دورك. Your turn. No, your turn. That way there's no interference. I will always be able to hear the person who wants to speak when I tell them when it's time for them to speak. So you can coordinate time, or you can make your antennas very, very complicated, so that you're choosing who you want to speak to when, and you can make your decoding very, very complicated. It all depends on the application, but those are the degrees of freedom you have. And no, you can decide to coordinate time, or you can decide to coordinate your antenna, make it very complicated. It changes its beam, what we call the beam of the antenna, to make it narrow and block out things in different directions, as opposed to being what we call like an omnidirectional antenna is the most accepting antenna that you can have. It'll accept signals from the same directions, from different directions with roughly the same gain. So back to the story of the receivers. And what sensitivity is, as we said, different people have the ability to hear signals that are lower level. So if I was to whisper to somebody who's like maybe 15 or 16 years old, and if we say that everybody's got about equal hearing and it maybe degrades over the years, definitely maybe someone who's 16 can hear better if they're not listening to loud music, just regular people, not someone whose hearing has been destroyed. They would have a better probability of hearing something that's at a lower power. As they get older, we have to add these hearing aids, right? These amplifiers. What they're doing is they're taking the signal in from the air, and it amplifies it before it's sent to the eardrum, so that to bring the power level up. And that's because the sensitivity is getting worse. Yani, what does sensitivity mean? Sensitivity means, what power do I have to hear in order for me to understand what was said? So that concept applies the same way. If I was to speak in a low enough voice, or if I had something that I can turn the volume down very low, eventually we'll start seeing the difference between us, who's who has what type of hearing. You know, can
If I
find
may
a hearing
emphasize,
test.
I think you could make out in difference, like the ability to be able to detect a signal. It's a sensitivity issue. How low can that receiver be able to detect the signal?
So just staying with the analogy of the hearing, it's the same concept as he's saying. Now, if I go to the other side, I just transmitted my signal. The guy on the other side heard it he brought it in with the antenna. It's at a certain power level. It's at the RF. It's already been degraded because over the distance as he's traveling, over a rate of 1 over the distance squared is the rate that the signal declines. But it's related to frequency, it's related to the wavelength, and we'll talk about that equation